and all the side of structures. So we'd like to keep it one. And I'm gonna choose. For now. I'm gonna delete those 46 PSF because otherwise we doubled it the self slab weight. So that load, I'm gonna put the 0. So for now, every slab has a 20 PSFs Compostelo, then 100 live load. So ETAP will calculate all the self weight. So one thing that appeared out, so maybe you have a two choice. You can make all the section property dimension correct in ETAPS. So let ETAPS manually calculate all the section member weight. Don't want to deal with it. Maybe you may just weight from the ETAPS. But while ETAPS calculate column and wall all the weight correctly, there is another way you could do it. But I think for now, I will just show you a more simple way. There is always different way to do this, but that maybe confuse you at this moment. So I just more focus on more simple way to do this. So all the slab now has 20 PSF superimposed dead load and 100 PSF live load. Corridor for now, let me see. Corridor doesn't have a live load for now. You could just ignore it, or you could add it later, right? But for now, this class for now, today's is more focused on composite floor framing design. I'll just keep loads outside of the core. And one thing that I mentioned it in the beginning, I'm gonna turn off the column. We're gonna assign additional line loads on the spandrel beams. You know, when you select it and then right click, you could only show selected object only. So I only just select and I'm gonna assign frame distribution disputed line load. There's a cotton wall load, so I'm gonna choose as compose that load. Yeah.
You keep going in and out. We can't really hear you.
Oh, okay. Okay. So up to here, I select. Can you hear me?
Yes,
we can hear you. I select the spandrel beams. Only show it. Okay. And I'm gonna assign the cotton wall weight as a line load. So flame load, and I'm gonna use a distributed line load. So 20 times floor height 15, 300 pound per foot. So since this is foot per foot, so I make a 0.3, right? This is 300 pound per foot. It's assigned to the composite dead load. So okay, so you see that additional cotton wall load. So we have composite dead load on the slab 20 PSF, live load 100 PSF, and also line load on the parameters only 300 pound per foot. Depends on material of the cotton wall or enclosures, obviously. So I think we are ready. I'm gonna run it. I'm gonna okay, right click. You could just turn all the object on.
Before you, Professor, before you run it, I had a quick question about the wall thicknesses. How thick are we supposed to make the walls? And because so the wall for the stairs I believe is 15 inches, and the wall for the elevator bay I think I made 18 inches. So they're two different sizes right now. So I just wanted to find out from you
Okay.
what we should do because I couldn't
Okay.
find anything in
Generally,
the building code.
mm-hmm. Yeah. So now this is all up to us, the engineer. We at this point we are focusing on gravity load framing, one floor study, right? We're not interested in wall thickness at this point. So for now, but layout importance because of load pass, but overall size and thickness is not really at this point the main uh, interest. But as we move down to the lateral system study, we need to size it based on thickness and also material strength. So since W1 and 5, I don't know the thickness, I'm going to go back since you point out. I'm going to open and see what thickness we assign of wall 1 or 12 inches. So I'm going to use the same thing, wall 12, E4. So wall thickness 12, concrete strength 4. So I usually see wall 18 and C4. 18, C4. So we need more 15 and C4 because since we currently have a 4,000, we are using 4,000 psi, but obviously we need more than that, thicker than that. So let me just reshape. So for now, okay, one thing, gravity wise, 12 inch usually okay for one story, but since we're gonna design 40-story building, our wall thickness is much thicker. So just for heads up, you can just see the overall layout of a core wall, right? Most outer wall, just circling outside wall. Yeah, like when you see that I-shaped flanges, right? Maybe you could see this I shape of the wall. It has bending moment inertia. Uh, that this flange thickness really play a very big role for your uh, stiffness, like steel section, same things, mechanics. So thickness, or especially moment about strong axis of this I shape. I think in order to make the stiffness bigger, I think increasing flange thickness is the most efficient way. The same analogies, since those all the core walls tied with a link beam, this is more work like a box. It's perforated box. So overall outside wall, most outer out most outer wall thickness is actually most efficient than just increasing the inner wall thickness. So for now, probably I'm gonna just leave it as it is, and then maybe Thursday I already built many different options and explain more and more a little bit of details because we haven't today is focusing on the floor framing yet only. So typically 12-inch thick wall is much stiff enough. So